Every year is a year for celebration of one of our greatest researchers and innovators, Christian Birkeland. Physics professor at the University of Oslo for many years, of course. His life and work continues to fascinate us more than 100 years after his death. Birkeland was the first scientist to realize that northern lights had something to do with electromagnetic storms from the sun. He was responsible for 60 new patents on everything from margarine and caviar to an electromagnetic cannon that led to the fertilizer. He was behind the fantastic innovation that enabled making the fertilizer, of course, by harvesting nitrogen from air. This discovery was basis for the foundation of Norsk Hydro and the industrial bonanza, I would say, at Rjukan, and later also, of course, Yara. Rjukan, I guess that's the biggest spin out of University of Oslo, isn't it? Every time I go through Rjukan, I think Christian Birkeland invented this. And it's important. It's a part of what a university should be. He also led the foundation for much of the modern research conducted in the field of space and solar physics. He was one of the first space scientists and is still an inspiration to a new generation of students and scientists at the University of Oslo, in Norway and globally, I would say. He showed us that when you pose big questions combined with ambitions to solve societal challenges, the innovation potential is huge. So he managed both the basic science and the application. And I think still that people know about also the more applied side of his work. At least we try to tell about this when we visit embassies and other things around the world from time to time, quite often. To honor Christian Birkeland's work, a yearly Birkeland lecture has been arranged here since 1987 with a couple of exceptions. It's a cooperation, as you already said, between the Norwegian Space Center, Yara, the Norwegian Academy for Science and Letters, and the University of Oslo. And it gives me great pleasure to introduce this year's Birkeland lecturer, Professor Michele Dougherty, from the Imperial College London, UK. Professor Dougherty was educated at the University of Natal, South Africa, where she was awarded a PhD in 1989. 1991, you moved to Imperial College London, became Professor of Space Physics in 2004 and Head of Department of Physics in 2018. Professor Dougherty has been involved in space exploration for nearly 30 years, and in 2008 she became only the second woman in more than a century to be awarded the Royal Society's Youth Medal. She is leading unmanned exploratory missions to Saturn and Jupiter and was the principal investigator of the magnetometer instrument on board the Cassini mission to Saturn, which led to the discovery of an atmosphere around one of Saturn's moons. Michele has contributed significantly to the UK space sector and was chair for the Science Programme Advisory Committee of the UK Space Agency from 2014 to 2016. Fellow of the Royal Society, was awarded the Royal Astronomical Society Geophysics Gold Medal in 2017, a Commander of British Empire in the 2018 New Year's Honours List, and received also Institute of Physics Richard Glazebrook Gold Medal and Prize. In the 2021 Birkeland lecture, Professor Dougherty will take us to Saturn, and we look forward to that. The title of the talk is The Cassini-Huygens Spacecraft Mission to Saturn and Its Moons. In his time, Christian Birkeland also caught interest in Saturn. And in some of his famous Tarella experiments, the planet in the vacuum chamber did not represent the Earth, but rather Saturn. He managed to produce rings in the equatorial plane around the planet. And Professor Dougherty, Michele, we look forward to your talk here today. Thank you for coming to this lecture. And the floor is yours.
Thank you very much. I never really recognize myself when I get described, but thank you. Before I show you my favorite image from the Cassini mission, I just wanted to put this slide up here to remind me to say that the first 2 papers I had published when I went to Imperial College, I didn't do 15 for my PhD, was linked to a discovery that we made from the Ulysses spacecraft that flew past Jupiter. We discovered Birkeland currents at Jupiter. And the second paper combined them with Hubble Space Telescope observations of the aurora. So I was working on field line currents and Birkeland currents right from when I first moved to London in 1991. Okay, so what I'm going to talk to you about today are some of the discoveries that were made by the Cassini-Huygens spacecraft, which went to the Saturn and Titan system. And the reason I like to start with this slide is it shows you the Saturn system in its entirety. It consists of lots of different images that were taken by the spacecraft, by the cameras on board the spacecraft, over a long period of time, put together. You can clearly see the planet itself. You can see the sun was behind the planet, so you can see the sun's rays coming from behind the planet. You can see its visible rings beautifully. You can see another ring called the E ring, and that's one of the rings that I'm going to talk about today. And embedded within that ring, you can see a moon. And that moon is called Enceladus, and that's the one where we discovered an atmosphere, or rather outgassing of water vapor. And you can also see the outgassing of water vapor taking place there. But last but not least, you can see the Earth. There's the Earth, peeping through the rings. And whenever I look at that, it makes the hair on my arm stand up on end, because there we were taking images of Saturn, and and those images were essentially taking images of us as well. So just a little bit of history. The first observations were made of Saturn by Galileo in 1610, and these are hand-drawn images or hand-drawn drawings that he drew as he looked at Saturn over a period of time. And he didn't quite understand what it was he was seeing, because every time he looked at Saturn, it looked different. And in fact, it took 45 years for Christian Huygens to realize that these were actually a set of rings. And so as Saturn orbits around the sun, it changes its inclination as it orbits. And so on occasion, its rings are sideways on and you can't see them. And other times, they're almost at a big angle and you can see them really clearly. So that's why it looked so different in all of those different views. And Christian Huygens, in fact, discovered Titan in the same year that he realized it was a set of rings. So the top view there shows you the first sketch of Saturn, and Huygens proposed that it was surrounded by a solid ring. In fact, we know now that ring isn't solid. Consists of countless individual particles, each in their own orbit around Saturn. And then there are a list of some of the other moons that were discovered as well. But in fact, the only thing I'll point to here is it was Cassini who discovered there was actually a gap between the rings. And that was the gap the Cassini spacecraft flew through as it went into orbit around Saturn. We hoped it was a gap, and it turned out that it was. So this shows you a view of all the different countries, all the different scientists and engineers that were involved in being able to be successful in having the Cassini-Huygens mission do what it did. My team was based in the United Kingdom. I had co-Is from the United States, from Germany, and from Hungary as well. And my instrument, whenever we can, is placed on a very long boom. So what the instrument does, it measures the magnetic field in the environment of the spacecraft. But we want to make sure we measure the environment and not the magnetic field from the spacecraft. So we try and put ourselves as far away as we can. And there were two instruments, one which was built at Imperial College, which was halfway down the boom, and one which was built at the Jet Propulsion Lab, which was right at the end of the boom. And in fact, a complication was the one at the end of the boom stopped working about a year after we got to Saturn. And that made our ability to calibrate the instrument much more complicated. And so, in fact, we rolled the entire spacecraft to let us calibrate. You can see the spacecraft covered with lots of gold foil. It acts as a thermal blanket to keep the instruments and the spacecraft at a temperature that they can actually operate at. And then, last but not least, you can see, second to last, you can see the Huygens probe, which was built by the European Space Agency, and which, when we arrived at Saturn, was detached and traveled down through the atmosphere of Titan and landed on the surface of Titan. And then, last but not least, you can see the high-gain antenna, this white umbrella-shaped object. What would happen is, once we got to Saturn, once a day, the high-gain antenna would point down at the Earth for 8 hours, and it would download all of the data that all the instruments had taken the previous day. Oh, I'm too quick. Much too quick. I lift my finger off quickly and that will work, but no. Okay. Okay, I will. I'd rather use this if I can, thank you. So this view here shows you the spacecraft in the test chamber before launch, and this is a test chamber which allowed us to test the instruments and the spacecraft could work in the vacuum that it would see in outer space, but also the range of temperatures that we were going to see. We flew past Venus, which was plus 40 degrees Celsius, and out at Saturn it was minus 170 degrees Celsius. So we needed to be able to operate at those range of temperatures. You can also see people standing in the test chamber, so you can see how large the spacecraft was. And what you can't see is the magnetometer boom sticking off from the side of the spacecraft. And that is, if you think about it, you can't launch a spacecraft with a large boom sticking off from the side. So what we did is we deployed the boom once we flew past the Earth. These were the two instruments that we built. So the one in the top left is a fluxgate magnetometer that was built at Imperial College, and the one on the bottom right was a vector helium scalar magnetometer that was built at the Jet Propulsion Lab. And it's the one on the bottom right that stopped operating. We think there was a small hole in the helium chamber, which is why it stopped operating. So this gives you a view looking down on the equatorial plane of the solar system to give you an idea about how we get a large spacecraft like Cassini out to the Saturn system. So here we have the Sun, we have Venus, the orbit of Venus here, and the orbit of the Earth here. And so after we were launched on the 15th of October, 1997, we had 2 flybys of Venus to give us enough energy and momentum to get us further out in the solar system. We had a flyby past the Earth in 1999, and that was when we deployed the magnetometer boom. And as we flew quite close to the Earth, we were able to measure the internal planetary field of the Earth that we know well. And so that allowed us to get an understanding of the calibration of the instrument. For us, we need to know where the zero level of the instrument is. So if we measure any small changes in the magnetic field, we know they're actually real. We then had a flyby past Jupiter in December 2000, and we finally reached Saturn on the 1st of July 2004. So you need lots of patience to be involved in outer planetary spacecraft missions. We were really busy on the way there, but it did feel like a very long 6.5 years. Okay, so I want to talk about 3 main topics this evening. One is Titan, the other is Enceladus, and then last but not least, I'm going to talk about the end of mission for Cassini. And I won't be able to go into much detail about Titan, but I did want to start on Titan. So this is a view of Titan that we had before the Cassini spacecraft got there. And this was taken by the Hubble Space Telescope. And the thing that you will notice is you can't see down on the surface. And that's because Titan has this dense hydrocarbon haze, which essentially doesn't allow us to see down on the surface. We knew there was a dense atmosphere. You can clearly see the blue region of the atmosphere there. But one of the reasons that we wanted to go to Titan, and not only did the Huygens probe travel down through the atmosphere and land on the surface, but the Cassini orbiter flew past Titan. By the end of the mission, it was about 120 times. So we have a much better understanding of Titan now. The reason we wanted to do that is that we thought that the chemistry in the atmosphere of Titan was very similar to what the early Earth's atmosphere was like. So in some ways, it was almost a way of going back in time so we can see how our atmosphere has evolved over time. This here shows you one of the first views that the imaging camera on board Cassini took of Titan when we first got there. You can clearly see the depth of the atmosphere. The atmosphere was about 950 kilometers in depth. And in fact, after some of the early Titan flybys, we were much more careful because the atmosphere was so dense. Because of the boom, we were concerned that the spacecraft might begin to tumble. So we had to be much more careful on the Titan flybys. And you can see that even with the spacecraft in orbit around Saturn, the visual camera was still finding it difficult to see surface features. We could see something, and they looked as though there was something reflective at the South Pole, but we were still unable to discern some of the details of the surface features. Now, one of the real surprises about Titan, for the first 5 years that the Cassini spacecraft was in orbit was the fact that we hadn't seen any liquid on the surface. Now, when the Huygens probe traveled down through the atmosphere and then landed on the surface, its cameras showed that they looked as though there were riverbeds and old lakes. And so we really expected quite early on to see liquid on the surface. Not liquid water, but liquid ethane or liquid methane. It took until 2009 before the visual infrared mapping spectrometer saw this glint of sunlight off a lake at the North Pole of Titan. And it took us a bit of time to work out why we hadn't seen it before. And that was because for the seasons on Titan, where the liquid was, hadn't been in the view of the sun. And so as Titan was orbiting around Saturn and as Saturn was orbiting around the sun, it wasn't the right season for us to see the liquid on the surface. And now we know that there are weather systems at both poles where we have liquid ethane and liquid methane raining out of storms in the atmosphere. But this was the first confirmation that we had that there was actually liquid on the surface. This here is a composite of 13 years worth of data from the same instrument that showed you the glint, which essentially allows us to see the entire globe of Titan. This region here called Xanadu was the only region which had been seen through the haze before the infrared images. And so this was that bright region that I showed you in the earlier image. You can clearly see in the equatorial regions there is this band of sand-like color, and that is in fact sand dunes, which seem to encircle most of the equatorial region. You can see regions where there are purple colors, that is water ice. There is an impact crater that you can see just there, and there is an ice volcano that you can see there. So there's a huge amount going on the surface. We now have a much better understanding, and there is now a focus on Titan. To go back to Titan, there will be a NASA mission called Dragonfly, which will consist of not only a spacecraft, but I think it's got a helicopter as well that's going to hover over one of the lakes. So there is now a real focus on trying to understand Titan better. But before I talk to you about my favorite moon of Saturn, let me just tell you, just put things into context so that when I show you the data that I do, you understand what it is that we're actually measuring. So this is a view of the Earth. If we were able to see the magnetic field lines of the Earth, they would look like these red lines that you can see here. And one way that I like to think about it is planets like the Earth and like Jupiter and Saturn, they have an internal planetary dynamo, which has currents flowing as a result, and those currents generate a magnetic field that we see outside. It's almost, one way to think about it is if you've got a bar magnet, if you had a piece of paper over the bar magnet and you put iron filings on top of that piece of paper, the iron filings would lie along the lines of force of the magnet. And so that's essentially what my instrument measures. It measures the magnetic field. One other thing I want you to keep in mind is as the planet rotates on its axis every day, those field lines are rotating at the same rate. And so if you are a moon, there, say, those field lines are going to move past you at the same rate as the planet is rotating. And I'm going to refer to that when I show you some of the data. Okay, so just to orient you, that shows you a side-on view of the Saturn system. You can clearly see all the visible rings. You can see the Cassini division, which is the gap through which the spacecraft flew when it first went into orbit around Saturn. And then you've got some moons in orbit beyond the visible rings. You've got Mimas, you've got Enceladus, and you've got Tethys. Now, Enceladus is embedded in this diffuse E-ring that I showed you in that first image right at the start. And something to keep in mind is that the particles in the rings are made up mainly of water ice. So the plan was that when we got to Saturn, about 6 months after we got there in 2005, there were 3 flybys of Enceladus by the Cassini spacecraft planned. And the flyby altitudes were the following. There was one just under 1,300 kilometers from the surface. A month later, there was a second flyby, which was 500 kilometers away. And then 4 months later, a third flyby was planned, which was originally going to be 1,000 kilometers above the surface. But based on what we saw on the first 2 flybys, we were able to persuade the Cassini project to take us much closer on that third flyby. And I'll show you the data that we used to be able to have that change made. But before I do that, so let's have a look at the surface of Enceladus. So it seems to be covered in craters and, cracks, ridges on the surface. What it isn't covered in is craters. There are a few craters on the surface. You can see them there. But if you compare the surface of Enceladus to the surface of Mimas and Tethys that orbit quite close by, those moons are completely covered in craters. And so the implication is that something is happening at Enceladus to resurface it. Something is making the surface much younger than you would expect it to be. And long before Cassini got there, scientists had wondered whether Enceladus was somehow the source of Saturn's E-ring, but they weren't quite sure how that could be the case. So you have to be a magnetometer person to get excited by this data. I promise I won't leave it up there long. I promise not to show any equations, but I did have to show a bit of data. You showed a really scary equation. I couldn't match that. Okay, so what we have here is 24 hours worth of data. We have the 3 components of the magnetic field, and we've got the magnitude of the magnetic field. So the magnetic field is a vector, so you can work out its 3 components and then work out the strength of a magnetic field from that. And if you look really closely, in this component there's a little pimple in the data, which is mirrored similarly in the strength of the magnetic field. But these 2 components, this top one and the third one, are really interesting. If you follow the behavior of the field, it seems to be doing that. And then something weird happens just there. And similarly here, the field seems to be decreasing, and something very different happens. In addition to that, you have an increase of wave activity, both before and after. And that was the flyby of Enceladus. An easier way to view that is if we look at it like this. So what I've done in this view here is I've subtracted the magnetic field of Saturn away from the data. So all we're looking at is the magnetic field due to Enceladus. So we're looking down on the north pole of Enceladus. Saturn is way off to the top of the page here. The magnetic field and the plasma from Saturn is coming in from the left. And this is the trajectory of the spacecraft. And overlain on top of that, those little vectors, is the signature of Enceladus. And it almost looks as if, as far as the magnetic field is concerned, Enceladus is a much bigger obstacle to the magnetic field. Something is stopping the magnetic field from penetrating down. So something is bending the magnetic field of Saturn around Enceladus and not allowing it to penetrate onto the surface. And I pointed out to you in the previous slide there was a large increase in wave activity. That was due to ion cyclotron waves, and we were able to calculate that it was water group ions. So as we approached Enceladus, there was a large increase of water group ions, and we had the strange signature that the magnetic field was bending around Enceladus. So to be able to visualize what we thought was happening, we put this little schematic, it's too important to call it a movie. But so there are 2 different views here. Here our eye is looking down on the north pole of Saturn. So there's the north pole of Saturn. Saturn is the yellow ball. The gold rings are the visible rings of Saturn. The blue lines are the magnetic field lines of Saturn that are rotating once a day. And the little orange ball is Enceladus as it's orbiting around Saturn. Now, if Enceladus was a dead body, the magnetic field of Saturn wouldn't see it at all and would move straight through it, just like we're seeing here. But instead, what we seem to be seeing was the following. So now we're looking sideways on. Here is Enceladus. The blue lines, the magnetic field lines of Saturn, are coming in from the left. And instead of going straight through Enceladus, they were being held upstream. Something was stopping them from penetrating down onto the surface and through the moon. One way you can do that is an atmosphere. If just like on the Earth, the upper regions of the atmosphere become ionized by solar radiation, and they protect us from the effects of the solar wind field because they drape around the Earth. So what we did is we put this schematic together here, which showed what we thought we were seeing based on the first 2 flybys. So we postulated that there was a diffuse extended atmosphere covering the entire surface. Now, this was based on 2 separate flybys. We were slightly concerned because the flybys had happened a month apart. It took a while for NASA to get us the spacecraft trajectory back in high resolution. And as we were flying past Enceladus, we were moving very quickly so the camera could stay in view all the time. And so we were slightly concerned we hadn't really calibrated the data properly. But the fact that we'd seen it on 2 flybys a month apart made us be brave enough to say that we thought we were seeing something. So I went out to the Jet Propulsion Lab to give a presentation to the scientists out there, because there was a science meeting at that time. And what I wanted to do was I wanted to persuade them that we thought we were seeing something really interesting, and persuade them to lower that 3rd flyby so it was much closer. And I was jet lagged to hell. I'd arrived the day before, and I was standing in the Starbucks line to get a coffee. And the man standing in the line in front of me, his name was Jerry Jones, and he was responsible for the spacecraft. And he turned to me and he said, "Hi, Michele, wasn't expecting to see you here." So I described the situation, and he rubbed his hands together in glee, and he said, "I've always wanted to go closer to a planetary body than anyone else." So I knew I had 1 vote in my back pocket when I went into the meeting. It was a difficult meeting, because one of the things about Cassini is we spent the 6.5 years it took us to get to Saturn, planning every second of every observation that we were going to make. So we knew exactly what we were going to do all the time. And if we were going to ask the project to change the trajectory of the spacecraft, that would mess up the observations that we wanted to make. We decided we would do it, though. There was enough interest in doing it that the project agreed that they would change the flyby. And fortuitously, the 3rd flyby was going to be just below the South Pole, with the closest approach being 173 kilometers above the surface. And I say fortuitously because what we found was, instead of there being an atmosphere covering the entire surface, there was an outgassing of water vapor just from the South Pole. Because we went so close, all the other instruments on board the spacecraft were able to take really great data as well, and I'm going to show you data from some of those. So this is 2 data sets. Top left is data from the imaging instrument on board, and you can clearly see cracks at the South Pole, which the imaging team called tiger stripes. So there were fractures into the interior. Bottom left is data from an instrument that's able to remotely sense the temperature of a body. And what they expected to see was the hottest region would be at the equator, because that's where the solar radiation is strongest. And they did find it was hotter at the equator, but they found a hot spot right at the South Pole. Now, when I'm talking about hot spot, this is all sort of relative here. We're talking about 85 degrees Kelvin instead of 75 degrees Kelvin, but that's quite hot for out at Saturn distance. If you overlay those 2 data sets on top of each other, the hottest spot was right over one of the cracks, so at 91 degrees Kelvin. So what we had at Enceladus was we had internal heat leaking out from the moon. Now, that was a real surprise. Enceladus is small. Its diameter is 500 kilometers. We had long assumed that it had cooled down from when it first formed. So we've got this internal heat source at Enceladus. So we've got water group ions as we flew past, an increase in water group ions, this heat source. This here was a view taken by the camera about 6 months after that first flyby, actually. And you can clearly see that there is quite a lot of structure in this plume. And it turns out it's not only water vapor that we're seeing, it's dust, and it's other material as well. But you can see there are individual sources from the different cracks. And in fact, as Enceladus orbited around Saturn and the tidal forces changed, the different cracks were opening and closing, and you sometimes had more outgassing than on other occasions. But for me, I think the most exciting discovery was the following. And that was by the eye-neutral mass spectrometer. So this was an instrument that was almost able to taste the environment that it flew through. And we flew through the plume. There was a very close flyby of the plume. I think it was 25 kilometers above the surface. And this is what was found in the plume. So there was water vapor, but we knew that was there anyway because the magnetometer data had showed that. There was methane. There was carbon dioxide, monoxide and carbon dioxide. But most importantly, there was simple organic and complex organic material. And if you're looking for life, if you're looking for potential habitability, you need there to be four things. You need there to be liquid water, which we now know we have in the interior of Enceladus. You need there to be a heat source. You need organic material. And then you need those first three things to be stable enough over a long enough period of time that something actually might happen. And so there was now a real focus on Enceladus as potentially having the ingredients for life to be able to form. And in fact, on a subsequent flyby, the same instruments discovered ammonia in the plume as well. And that might be one way of keeping the water liquid, because ammonia almost acts as an antifreeze out at those kind of distances. So that's one thought as to why it's not frozen solid. Okay. Let me move on to JUICE briefly. JUICE is what we're working on at the moment. The reason I don't want to do JUICE at the end is I want to end with a movie of the end of mission of Cassini, and it's much nicer to do it in this order. So I think one of the most important discoveries or realizations that has been made in the last 30 years in planetary science is the fact that you don't need to be close to the sun or close to your parent star for there to be liquid water. So prior to the Galileo spacecraft and then the Cassini spacecraft, we always thought that if you were looking for habitable environments, you needed to look on the surface of a planetary body because that's the way that you're going to get liquid water. What we have found in the last 30 years is you can actually go beyond the snow line, so beyond where water is liquid on the surface, where it is frozen on the surface. And you can find environments both at Jupiter, the moons of Jupiter, and at Saturn, where you can have liquid water underneath the surfaces. And so this is part of the case that we made to the European Space Agency when we were trying to get them to select JUICE, the mission to Jupiter, as the first large class mission, was that we would essentially be able to focus on these moons. So the focus of JUICE is going to be not only Jupiter itself, but the three moons of Europa, Ganymede, and Callisto. And all three of these, we're almost certain, have got liquid water underneath the surface, based on observations that the Galileo spacecraft made. And I think one of my subsequent slides shows you what we think the interior structure of these moons look like, based on the Galileo data. But in addition to that, they allow you to get an understanding of two different types of bodies. We think that Europa is much more Earth-like, where the liquid water is close to the surface. But we think that Ganymede and Callisto are a new type of body known as a water world, where there are different layers of water. So there might be a deep ice crust, and then a layer of water, and then another ice crust. And we think that there are many such bodies in orbit around exoplanets. And so we see focusing on these moons as one way of getting an understanding of this new type of planetary body. So this is the one I referred to. This is the interior structure that we think these moons look like. So Io is a very strange beast. Io is the one that has sulfur volcanoes on the surface and spews out a ton of sulfur a second. So to be frank, we're staying away from Io. It's a scary place to go as far as a spacecraft is concerned, especially if you wanted to survive any length of time. Europa is going to be a focus for us in the sense we're going to have 2 early flybys of Europa, but NASA is actually sending the Europa Clipper mission to Europa, and they will have multiple flybys of Europa. So as far as JUICE is concerned, we're going to focus not only on Ganymede, but on Callisto as well. And one of the things we want to try and understand is why is one undifferentiated and one differentiated? They were formed at the same time. What's happened in their past to make them different? And then as far as a magnetometer person is concerned, Ganymede's probably the most exciting place you can go in the solar system because it has its own internal dynamo field, the only moon in the solar system that does. And in addition to that, it's embedded in the background magnetic field of Jupiter, which is changing all the time. And what that does is it induces electrical currents to flow in the ocean, and we will then be able to measure those currents. And in fact, if I lose sleep about JUICE, it's whether we're going to be able to resolve these very small changes in the magnetic field. One way I like to describe it is it's like trying to measure or trying to view needles in a haystack, and those needles are changing shape and color all the time. So that's what I lose sleep about. But at the moment, we're still just finishing off building the instrument. So I've got many years ahead of me to worry about that. So this shows you a view of JUICE, and one of the reasons I like to show this today is you can very clearly see the field line currents from Jupiter attaching to Io. There's actually, in the auroral region at Jupiter, there's a Io hotspot that you can see moving in the auroral zone. And in fact, we have something similar at Ganymede as well. You have the magnetic field lines from Jupiter connected to Ganymede, and you can see field line currents flowing between them. But JUICE is going to use solar power, and so this shows you an artist's impression of the spacecraft with its extremely large solar panels. And I think for me, the thing I've been most proud of in what we've achieved in lockdown is that we were able to build our flight instrument. So in March of last year, all of our labs were closed. My engineers took some of the bits home with them, and they were building the instrument on the kitchen table. But that didn't last long, luckily. We were able to start reopening our research labs in June of last year. And we, in fact, delivered our instrument to ESA a couple of months ago, and it's being put on the spacecraft at the moment. But it consists of 3 different instruments. So there's one here, which is built at Imperial College. Another one is built by our German colleagues in Braunschweig. And then last but not least, there's a scalar sensor, which is going right on the end of the boom, and that's built by our colleagues in Graz. And this is the electronics box, which is in the main body of the spacecraft, which will protect it from the radiation environment. This shows you the electronics box on the vibration table. We've got to make sure that it will survive launch. It was scary. You try not to watch. And then here it's hit by a large hammer just to see if it survives as well. That I couldn't watch at all. I had to wait and be told it was all right afterwards. So that's, in some senses, my research future. JUICE will be launched in August of next year. It'll take 8.5 years to get there. I won't tell you how old I'll be, but it will get there when I still, I'm sure, interested in doing research, and I can't wait to see what we discover with JUICE. But let me move on to the grand finale orbits for Cassini. So Cassini spent 13 years in total orbiting around Saturn. We knew we were running out of fuel, so about 11 years into the mission, we knew we were beginning to run out of fuel. And so we had to make a decision how we would end the mission. Did we want to put it into an orbit where it just continued to take data for many years and then slowly moved closer to Saturn and burnt up in the atmosphere? Or did we want to do something that would allow us to really understand some of the science that we hadn't understood from the first 12.5 years of the mission? And what we decided to do was to focus on Saturn. Now, one of the things about the internal magnetic field of Saturn is, before we got there with Cassini, we were really quite surprised. Planetary dynamo theory tells you that if you have a magnetic field generated in the interior, the rotation axis of the planet and the dipole axis of the magnetic field, there needs to be a tilt between them. There needs to be that tilt for the magnetic field to continue to be formed. And before we got to Saturn with Cassini, we had measured the tilt with Pioneer and Voyager spacecraft, and it was less than 1 degree, and that was a real surprise. On the Earth, it's of order 20 degrees. On Jupiter, it's of order 10 degrees. And so we didn't we thought maybe the rings of Saturn were somehow masking the effect of the internal field, because we know there is an ionosphere in the rings, and they might generate a field of their own and therefore be masking the effect. And so before we got to Saturn, we said, once we get into orbit, we'll understand. All it did for us was that it made the angle even smaller. So by the time we got to the end of the mission, we knew it was less than 0.1 degree. And that we didn't understand. So I said, let us get inside the rings and we'll solve it all. I've got to be really careful what I say. But anyway, so what we did is we planned, this is the last year of the mission. We used Titan, this is the orbit of Titan, to get the spacecraft up out of the equatorial plane, and there were two phases to it. There was the ring grazing orbit, where the closest approach was just beyond the edge of the visible rings. And then the last 6 months of the orbit showed these grand finale orbits, where we were inside of the rings, just above the atmosphere. And what you can't see here are the magnetic field lines of Saturn. But in fact, these ring grazing orbits were critical for us because they allowed us to measure the field line currents, so the Birkeland currents, on every single orbit. Because we needed to be able to model those so that when we got really close, we could subtract their effects away from the data and just focus on the interior of the planet. And so, it was really great that we had planned the end of the mission the way that it was. So this just as a close-up view, it shows you we were about 3,000 kilometers above the cloud tops. But the reason I show this here is it makes it very clear to you that the rings are not solid. You can see through the rings. Some of them are a bit deeper than others, but they're really rather tenuous. Now, the reason, and I alluded to this a little bit earlier, the reason we wanted to get in so close to Saturn is we wanted to try and get an understanding about what was going on in the interior. We thought we knew before the Cassini observations that a planetary dynamo is generated really by two things. You've got the deep rotation in the interior, and you've got heat being given off. You've got an overturning, bubbling motion, almost like porridge bubbling on a stove. You have that kind of motion. And the combination of those two things generates the planetary dynamo. But it can only continue to be generated if you have this tilt between the rotation axis and the dipole axis. And so we planned to spend 6 months in really close orbit. And this here shows you a view, an artist's impression of the spacecraft at the start of that first deep dive. And so what we decided to do is that we would travel with the high-gain antenna pointing in the direction of travel. So if there was any energetic dust or any energetic material, it would maybe make a hole in the high-gain antenna, but wouldn't ruin any of the instruments. And I remember I went out to the Jet Propulsion Lab for this first deep dive, and the project manager was walking around sweating. He was looking really nervous. And he said to me, "Oh, Michele, I'm so scared for your instrument." He said, "Because you aren't protected by the spacecraft." And I said, "I know, Earl. I'm trying not to think about it. There we were waiting to be hit by whatever energetic dust was there. Turns out it was empty. This gap was empty. And so we were able to safely do 22 of these orbits. This here shows you where the spacecraft dived into the atmosphere. So this is a view from the infrared instrument again, and what it was able to measure was essentially the internal heat coming from Saturn itself, and that's where the spacecraft went into the atmosphere. Just to give you an orientation, it went into the atmosphere just above the equatorial plane there. This shows a view from the mission control just after the end of the mission. It was really interesting, We were all exhausted. We had a very close flyby of Saturn every 6.5 days. And we didn't think we could keep it up. We were really tired. We just wanted to rest. And so some of us were actually almost relieved that it was almost over. And then we saw this, and we thought, oh my gosh, I've spent the last 25 years doing this. What am I going to do with myself now? But for me, the most poignant moment was this data here. So if you look at these two curves here, that spike, those two spikes tell you that the spacecraft is talking to the Earth. When those spikes disappear, it means the spacecraft isn't there anymore. So we were all watching it avidly. The spike disappeared, and then it came back again. And the reason that it came back again is no one had told Cassini it was the end of the mission. And Cassini had been programmed to keep in touch with the Earth. So it moved itself, so it could continue to talk. And we thought, oh, it'll be fine, and then it disappeared, and then that was it. So let me end by showing you a movie that NASA put together. They put this together 6 months before the end of the mission, and everything that they predicted was going to happen happened.
A lone explorer. On a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini spacecraft is running out of fuel. And so, to protect moons of Saturn that could have conditions suitable for life, a spectacular end has been planned for this long-lived traveler from Earth.
5, 4, 3, 2, 1, and liftoff of the Cassini spacecraft on a billion-mile trek to Saturn. We have cleared the tower. Its program is in. All program is in.
In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
The SOI burn attitude or pointing position and light up the rockets.
The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system.
Huygens arrival on Saturn's moon Titan.
For over a decade, Cassini has shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. Now, Cassini has one last daring assignment. Cassini's grand finale is a brand new adventure. 22 dives through the space between Saturn and its rings. As it repeatedly braves this unexplored region, Cassini seeks new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends, as Cassini becomes part of the planet itself.
I'll stop there. Thank you very much.